Okay. So, we covered this recursive least squares lattice filter at length. We derived the entire algorithm. There was both order updating and time updating. The delta, there was that delta Pn, the inner product between two prediction vectors, that was to be time updated because that can't be order updated. Okay, but variances of the backward and forward error forward prediction error vectors, those could be, this norm square rather, norm square could be could be time order updated. Okay, and in that order update relation, we found out that one term comes in the denominator, which has the potential of becoming 0. That is, of course, another term also comes. The two terms that come are the norm square of the forward prediction error vector and backward prediction error vector. But of these two, the backward prediction error vector can become 0 if, while by the order updating process at a very early stage, that is when the time index n is much less, and you are doing order updating, then a stage may come when an all 0 vector could be projected on some space, on the future space, and error taken. So, that will give rise to an all 0 backward prediction error vector whose norm square is 0, that will come in the denominator, division by 0 might come up. That is what the linear dependence would reveal here. So, to avoid that, I added in the initial condition phase one very small constant delta as the initial value of backward prediction error vectors, initial value of the norm square, that is norm square of the backward prediction error vectors, that is sigma p b minus 1, sigma p minus 1 b whole square, that is at n equal to minus 1, the initial value sigma p comma minus 1 superscript b whole square, that I took to be delta, where delta is a very positive but very small quantity. And then you can see, you just take n equal to 0, then n equal to 1, n equal to 2, and see some stages how that backward prediction error, as you go further along the stages in the order update process, you will see even at n equal to 2 or n equal to 1 or n equal to 3, as you increase the order, you will see that, you will see the mechanism, you will see that backward prediction error vector norm square is still remaining 0 otherwise, but it is not here, here it will be equal to delta. So, the delta will always propagate, it will make sure that division by 0 does not come. I am not going to that thing, it is just, you have to just run the recursion manually, take 1 or 2, n equal to 0, n equal to 1, n equal to 2 say, and few stages, p equal to 1, p equal to 2, p equal to, and then you will see that even when the backward prediction error vector is ideally 0, and therefore the norm square is ideally 0, the delta will be there as an offset. That is how the division by 0 thing is taken care of there. Then towards the end of the previous day, I told you about a new topic called QR factorization. Q is a unitary matrix, R is an upper triangular matrix, QR factorization. Okay, recursive least squares using QR factorization, that is what I will concentrate on today. Suppose, so I will just start with the basics of what is QR and all that. Okay, even for the time being, forget adaptive filter. It is again numerical linear algebra, very useful in solving linear equation, developing fast algorithm for solving equations and all that actually. Suppose I again using the same notation, I have got a matrix X of columns x1, x2 dot 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 say x m, and each one is a column vector. So, in general x k vector will be what? X k 1, shall I use this way, or maybe x k 1 dot 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 x k some index n, so total number of row is small n. Consider small n number of rows to be higher than capital N, and that will always happen, because this will be data my vectors, and data as time index, because n is increasing always. So, naturally after some time, I mean, you will definitely have situations where length of this vector will remain higher than m, because as time moves the length will grow. So, for the time being take small n to be greater than m, that will ensure that linear independence is not violated, because the moment you take number of row less than number of column, I have the problem that all the vectors are not, I mean, they do not form a linearly independent set, there is some redundancy. I want to avoid that here. Okay, I will come back to the dependency thing again later, when some algorithm, but for the time being assume that n, there is a number of row, n is an index. Actually, in the filtering context, it will actually amount to time index, but here it gives you the number of row that is higher than, we assume that n is greater than equal to m, and also the columns are, they are linearly independent, they are Li, linearly independent, it is given. So, I have got a perfectly linearly independent set. For that only I need n greater than equal to m, obviously. Now, suppose I want to do Gram-Schmidt orthogonalization of this, and then orthonormalization also, so that each of the orthogonal vectors that come out of it has a unit norm. That is not a problem. Okay. What I will do? I will take x 1 as it is. Again, there is nothing unique about it. I could start with x m or any other vector, then go on building. I will start with say x 1. X 1 as it is, x 1 will give rise to just x 1 by say k 1, where k 1 is norm square of, in fact, norm. It is not be square, it should be square root of norm square. So, k 1 with a positive number, this is a positive thing. Huh? So, x 1, from x 1 I get a vector with unit norm. So, then x 2, I have to generate that orthogonal, a set of orthogonal bases, I mean basis vectors out of this. We all are familiar with Gram-Schmidt. What will I do here? Take x 2, project it on this guy and take the error, and then divide by the norm square of the error to make it unit norm. So, that means I will get x 2 this should be, I should have a prime here. This is a new vector I am developing. It cannot be x 1. X 1 prime. From x 1 I develop the first orthogonal basis vector, which is x 1 prime, this unit norm. Then I develop x 2 prime. How do I develop x 2 prime? First x 2 and some, it should be minus, but I am just putting it plus for the time being. Some constant times x 1. What is the constant? Inner product, that we know, inner product between x 2 and x 1 divided by, here it is no problem, some constant, but that constant formula here is not, I mean, I am not much bothered about that nature of the, it will be some constant. Okay. Say a 2 1 into x 1, this is the vector, and then divide by norm of the above, this thing, norm of above. That is 1 by, if you call this quantity k 2, this is 1 by k 2 plus a 2 1 by k 2 times, sorry, not this way. I immediately saw a frown from Joydev actually, he was frowning, how can I put them in the same bracket? Yeah, I will not do that, x 2 and a 2 1 by k 2 into x 1. See the structure, first see these two, I will do one more and then you will get the circle. X 1, I had x 1 is just divided by k 1, that gives you this. I had x 2, from that how do I get this? X 2 and x 1 they are linearly combined, and that is how I get. But what is the form of linear combination? X 2 fellow get 1 by a constant, this fellow gets something by the same constant. Okay. Now, remember this cannot be 0 because x 2 is not lying in the space spanned by x 1. Okay. Then x 3 prime, this is the last, after this the pattern will emerge. X 3 prime will be what? X 3, essential thing is the person you are targeting, that vector remains as it is not multiplied, like here not multiplied by 1, here multiplied by 1, here multiplied by 1, just a norm will come in bottom. X 3 plus some constant, say A 3 1 x 1, A 3 2 x 2 divided by norm of the thing, and this you call K 3. Okay, so on and so forth. Okay, this is the structure. So, that means if I put these vectors like this, in this page only let me do. If I put the vectors, the orthogonal vectors, x 1 prime, x 2 prime, x 3 prime, dot dot dot, x m prime, that will be this x. Since I am having a shortage of space, I am not rewriting the entire x, is this x times one matrix of this form 1 by k 1 1 0 0 0 0 first, rest I am writing, but 1 by k 1 1 0 0 0 0, isn't it? How to do matrix vector multiplication? You know, you have to linearly combine the columns by these elements. The zeros will multiply these fellows, forget that, 1 by k 1 1 times x 1, that is what you get at x 1 prime. Okay. Then x 2 prime will be what? 1 by k 2 2, right, and here something, I am not writing some star, but then 0, essential thing is these zeros. Then again it will be some element here, some star, again 1 by k 3 3 0 dot dot 0, so on and so forth. So, what kind of structure is coming? An upper triangular matrix on top. Upper triangular matrix size is m cross m. Below that there is a chunk of zeros. Very simple. This upper triangular matrix, maybe with the chunk, for the time being with the chunk of zeros only, I will call R. Together R. Actually, the problem is, books sometimes take these to be R and write it as R and 0. Okay. Or maybe if you or for the time being, let me put this way, QR. Okay. If I switch over later, change the notation later, then take this only this upper triangular part, or will there be confusion, or maybe. So, let me write this way, x R and 0. Okay. This matrix I can call Q. This is not a square matrix. This is not a square matrix, but one thing is there, all the columns are they are mutually orthogonal. So, Q Hermitian Q will be not Q Hermitian, Q Hermitian you cannot do that product, it is not a square matrix. Q Hermitian Q, that will be, no, that matrix will be Q Hermitian Q means this column will come as row with Hermitian, I mean this column all are real. So, Hermitian and transpose are same, so don't bring complex here. So, here you have got x 1 prime vector, here you have got the corresponding row vector, their product will be 1. Identity matrix, isn't it? So, Q is an unitary, generalized unitary matrix, not a square matrix, but a rectangular unitary matrix. Q transpose or Q Hermitian, Hermitian transpose, they are same here because we are considering real data. Q transpose Q is I. Okay.
The columns of Q are orthonormal.
Yeah. So, Q transpose Q, but not Q Q transpose. It is not a square matrix. That is why Q transpose Q is permissible, not Q Q transpose. Always, whenever you have unitary matrix, we show Q transpose Q is I. Row times column, the inner product is either 1 or 0 that way. And since if they are square, Q transpose Q I means if the two square matrices A and B are such, A B is I, then it can be proved in linear algebra easily that B A also I. Using that, we say that Q into Q transpose also I. That follows from that, but Q transpose Q is I. That comes from unitariness, which is not, which does not require the matrices to be square. That applies here. Okay. Now, for the time being, let us do this QS X R 0. Let us call this to be QR decomposition. Actually, it is not X to be, X will be some form of this kind of form QR, some Q, some R, may not be exactly this, but that comes from this. For the time being, we will see that given a data matrix, we can write it this way. Okay. X into R, that is Q. Question is how to get R? Obviously, you have to first find out K 1. That means, you have to take the entire vector, find its norm square. Then after that, you have to find out A 2 1 or the inner product, and then again norm, and all those things will be there. And suppose this this is actually time index, and you have to do this business at every index. So, at every index of time, you have to compute this R. R will be every matrix will be a function of n then, R n, Q n, Q as a function of n, R as a function of n, right? You have to do it. So, that means, there is too much of computation, and computation will grow exponentially with time, because as n increases, inner product length also increases, isn't it? So, that is not doable, that is not a practical way. But there are ways, smart ways to get this R from given X. Q essentially, we actually explicit form of Q we do not need. The fact that Q is unitary, that is enough, that fact we will be using. We will be using this R. How at all that is coming? But you can't look for this, that okay, at every index I will find out a new R by brute force computation. That is ridiculous, that you cannot do. So, that business you have to do adaptive. Okay. I am just giving a hint beforehand actually. I have not even brought you to the context where this is, I mean, what is the relevance of this vis-a-vis adaptive filter or optimal filter, all that. Okay, that I will do. One way of doing this R computation, there are several ways. One smart way is by a technique called Given's rotation, which can be made adaptive and which basically leads to a very nice implementation on something called systolic array. When I apply Given's rotation to this kind of thing in context of adaptive filter, that entire thing can be realized on systolic array. Systolic array is a very regular array of some unit processors. Okay. This is a regular pattern, local connections only, all processors are pipeline, I mean there are pipelining latches between processors very fast. Okay. Unfortunately, I cannot tell about systolic array here. I mean, those who have done my course earlier, they know it at length, but this will relate to specifically QR is look for those kind of adaptive filter applications where you have got number of taps and number of coefficients to be very huge, and the computation, because very huge means per sample output computation, weight update computation, all those things require too much of complexity. So, they are for parallelizing the computation, for reducing the computational overhead, we go for this. Given's rotation I will come little later today, but that will take time. It is a beautiful thing, but it will take time. Let us first consider its application in the this case, adaptive filter case. So, then x 1 will be a x 1 within bracket n, a vector, instead of x 1 it will be x 1 n, x 2 will be x 2 n. In the adaptive filter case that we studied, x 2 n will be z inverse x 1 n, x 3 n will be z inverse to x 1, z inverse to x 1 n, and so on and so forth. That is what we, but I will still try to be more general here. I will call them separate column vectors, no problem. Okay. So, x1n, x2n, dot 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 xmn. So, this will be capital X n. M is fixed, it is not order recursive. Okay, it is a fixed order case. Xm, xn, sorry, that is the thing. So, now I have got one desired response vector dn. Yeah, please, all questions are welcome. Tell me. I may say me, yeah.
So then is it R and 0 below or 0 to the right of R?
Huh?
Left of R.
Oh, just a minute, you are right.
If you go to the other side, right?
Just a minute, I made one mistake here, because number of columns is m, isn't it? In fact, the zeros don't come. Zeros won't come here. Sorry. Thank you. Zeros should not come here. Are zeros required? We don't need. Zeros will come in this when I go here in the adaptive field. That's why I brought it forward from there. In this case, zeros won't come. Actually, when I do Gibbs notation, you will see the chunk of 0 will come. So, I shouldn't have brought it forward here. In this context, zeros don't come actually. That's making you have kept quiet, and I also made this mistake. Zeros don't come. It's smart of him that he has found out. Okay. This chunk of zeros don't come. I just have a zeros in mind. Actually, there is something called annihilation of column row and forming a 0 row, and therefore, a chunk of 0 rows will come. So, that is a target actually, this Gibbs notation thing. So, somehow that got carried here, is not. Just let us take a relook here. Thank you. Yeah. Let us take a relook here. X this 1 by k 1 1 0 0 0. So, 1 by k 1 1 multiplies x 1, fine. Zeros don't come easily, you see. Zeros don't come. I just a slip of tongue actually. Then this 1 by k 2 2, 1 by k 2. It's not k 2 2, k 1, k 2, k 3. Anyway, 1 by k 2, 1 by k 3, and these terms. These zeros will take care that okay, here 1 by k 1 multiplies x 1 prime x 1, then something which in this case actually a 2 1 by k 2 comes here, some data that multiplies first guy x 1, and 1 by k 2 multiplies this guy. So, it is just an upper triangular structure, square matrix actually. You should have stopped me there only. I mean, I didn't notice. I will come to this. There is something more that comes to my mind now in this context, looking at the structure. I will come to that soon, but let me come back to the adaptive filter case, or maybe here only I say this. In this context, I complete this and come to adaptive filter case. In this context, what I found? Q as X R. Okay. R is a strictly upper triangular matrix, no chunk of zeros. Okay. R is a strictly upper triangular matrix. Then X will be Q R inverse, and R inverse you call say R prime, and R prime also will be upper triangular. That is why it is actually called QR factorization of x, though we will be needing this form, not this form, but this is called QR factorization. Why the inverse of an upper triangular matrix? Upper triangular matrix must have non-zero diagonal entries, otherwise determinant will be 0, it is not invertible. So, that will come here, obviously you know the 1 by k 1 1, 1 by k 2 2, and they are not becoming zeros, okay, and they are perfectly linearly independent. So, this will be invertible. But upper triangular matrix's inverse is upper triangular. Lower triangular matrix's inverse is lower triangular. Anyway, those who are not able to see, take it. So, next time we will do it. We will take a class tomorrow actually. I will announce because we missed a class on Tuesday, tomorrow at 3:30. So, that time we will see. Just take it as a problem. It is not a problem actually, just to see how it comes, because I will not be using this form as I told you. It is just for academic interest. This form I am not so much bothered, but this is how it is called. X, any given matrix is QR factorized, where Q is a rectangular, your unitary matrix. Rectangular means number of row greater than equal to number of columns, that way, and this R prime is an upper triangular matrix. Okay. we will be using this form. Now, R prime is R inverse, R is invertible. If R is upper triangular, how R prime is upper triangular? You just, it is not difficult, you take it home. Okay. This is not coming in our business, so I am not bothered about that now. Now, coming to the adaptive filtering problem. Maiti pointed out, but again you did not say that zeros are not required. You said zeros to put the right, zeros are not required. It is a serious mistake. I should never overlooked it. Anyway, this is given to you x n, sorry. I have got a desired response vector d0, d1 dot 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 say d n, any general vector x k n, any column vector is typically of this form x k. Now, did I put 0 here earlier within bracket in the RLS lattice case, or 0 in the subscript within bracket? So, within bracket. Okay, this is the thing, this is your desired response. I want to find out a set of optimal filter optimal combiner coefficients, say C n as C 1 n dot 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 C m n, so that this error vector E n, which is d n minus x n C n, norm square of that is minimized. Of course, we all know all that it will be orthogonal projection, exists, unique, okay, or alternatively the norm square will be a quadratic function of the combiner coefficients, unique minima, you can find out. Okay, what is the norm square? Norm square will be, take the vector E transpose n, that is norm square, but we are using the generalized norm square here with that forgetting factor lambda. This is E n, okay, but we are not simply taking E transpose n E n, we have that lambda thing. Okay. That is, if you have forgotten, E square n plus, this is a repetition actually, plus lambda to the power n E square 0, isn't it? Yeah, this is the norm, and this we can write as E transpose n. This we have done in the lattice case, so you should not get confused. Okay. That time I gave a name to this matrix. What is the name I gave? Anyway, don't need E transpose n. This matrix I can say, this can be written as lambda half n, lambda half n. You can define two lambda, this is one matrix, this is just a notation, this is a notation. What is this? This is a diagonal matrix. Instead of lambda, I have got square root of lambda, positive square root. So, you understand, if you multiply the two, you will get this. This is a diagonal matrix by definition, this is a diagonal matrix by definition. What are the entries? Entries here, I mean same as this, but lambda replaced by positive square root of lambda. If you consider such diagonal matrices multiply, you get back this. Okay. And diagonal matrices are symmetric matrices also. So, then this norm square you can write as, you can easily see, what is this norm square? This quantity transpose times this quantity, E transpose n, transpose of this which is itself, then this, isn't it? So, actually this is a more generalized norm square, it is not simply norm square of E n, but norm E n pre multiplied by a diagonal matrix of this kind, okay, norm square, then the usual norm square of that. The point is, if I find out some unitary matrix, these are this vector, what to say, length n plus 1 vector, isn't it, E0, E1 up to En. So, this is length n plus 1 vector. If I have a suppose unitary matrix Q, square unitary matrix Q, and instead of this I take this quantity q into this. Q is a unitary matrix, q n plus 1 into n plus 1. This is any matrix. Very soon I will start using q and make it a function of n, because I will be indeed bothered about a q and that has to be evaluated at every index n. So, here just I am showing a result, so I am just taking a general q only, n plus 1 unitary. Then these two norm square are same, can you see that? Very simple. What is the norm square of this vector? Transpose of this into itself. So, E transpose n, this guy diagonal remains as q transpose followed by q transpose q is I. Remember, unitary of matrices or unitary operators in more general vector space sense, they all are always norm preserving. It can also be shown, I was trying to work out in the morning, it requires some more result. Any norm preserving operator is in unitary, at least for real and complex fields. That is when the scalars are real and complex, operators which preserve norms. Transformations, taking a vector, either abstract vector or this kind of column vectors, transform it to another vector, if they preserve the norm, then they are unitary, the matrices. Of course, the transformation has to maintain the length also. You cannot take that, okay, I take a length 10 vector, make it length 5, but norms are same. I am not talking of that. Okay, our transformation which takes a vector space maps it to itself, and there if it is norm preserving, it is unitary, and vice versa. If it is unitary, it preserves norm. That I will not prove. This part is very simple. This we have proved. So, any norm square remains invariant to unitary transformation of the vector constant. Okay. Can you give some examples of unitary transformations of physical this vectors? Don't bring that. That way, so any transforms we deal with that unitary. That one day I told you also when I was discussing orthogonal basis and all. I told you, I give some examples of DFT basis, Walsh-Hadamard basis, didn't I, in this class? So, they are unitary transform, but forget that. I am saying that in real life world, say in 3-dimensional physical world, there are vectors, not abstract vectors, simply x comma y, x followed by y followed by z, that kind of vectors. So, vectors of length 3. If you want to map it to another vector of the same size, you have to multiply it by linear operator, you have to multiply it by matrix, pre-multiply by matrix of size 3 by 3. That is the linear operator here. Suggest some unitary operator, or you can find a non-preserving operator.
So in 2 dimension, the rotation.
Oh, in 3 dimension, rotation is 1. You rotate a vector, its length does not change. That is, rotation is what we will be dealing with. Rotation is unitary. Translation. Oh, I am talking of operation on a vector. Rotation, reflection. There are these operators, they are, you can work out the operators, they are unitary operator. We will be considering rotation in particular, definitely. Okay. But anyway, so our purpose will be to find out some appropriate q at each index n, and appropriate in what sense, that I am coming now. I do not think I can consider Gibbs notation today, the time is running away, but it is a very interesting topic. It is a very, visually, you can easily understand, what is happening. Okay. So, suppose instead of q, I call it q of n. I call it q of n. That is the only thing I will say, because I am starting at my matrices are dependent on n, combiner coefficients looking for, they will be dependent on n, isn't it? Norm square is a norm square at nth index. So, the matrix q I will be looking for, it is appropriate that we should make it a function of n. If it becomes independent of n, then we will drop the index n. Okay. So, q n. How to choose q n? Q n is unitary and square unitary. And if I put a q n here, I will minimize the norms, this norm square, that will give me the same solution. About that there is no problem, because the two norm square are same. Okay. Now, this is a quantity. Yeah? I know this En is this Dn minus this fellow. I replace En by that. So, this lambda half n times dn one vector, lambda half n times xn into cn another vector. That is, I am now minimizing qn into minus qn into x and cn, right. This norm square, I have just expanded it. For the time being, you concentrate on this. I will choose q from this side, not from this. Whatever q comes out, that will be simply used here. This is normally when you do not use the lambda, this matrix is not there. But since it is there, it is diagonal matrix, you consider these two together, and you can even, for your convenience, you can give it a name, say x prime n or something like that, just for, so that I do not have to always say this into this x prime n. And assume the index n to be, of course, greater than or equal to m, that is always there, otherwise linear independence that will not be, will be violated automatically, that is always there. That how to take care of situations where n is less than m, that we will do separately, that is our observation. qn I will choose so that it does qr factorization of this. That is, there is one small difference, that is have to come back to that qr here. This matrix qn, that time qn was just rectangular, m number of column vectors to m number of orthonormal column vectors. But here I said the qn I am looking for is square. The QA that I am looking for is square. So, that is why that is what I was goofed up that time actually. I tried to do too many things at a time. So, let us come back to this once again. That time I had m columns and x also had m columns. So, obviously, there is an upper triangular matrix 1 times first column, then this, then 2 non-zero element, 3 non-zero element, dot 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 like that, and I get this. But x actually each matrix is of length say n plus 1 here. So, that the vector space has dimension n plus 1, out of which I am getting only m vectors, okay, out of which I am getting only m vectors. But there is nothing wrong, I can have extra vectors also. All the things they will not be obtained from these guys, but if you have got this x 1 prime n, x 1 prime, x 2 prime up to x prime, and from that I can take the space spanned by them and go outside that, still living in the main vector space, get a vector, project it, or I mean project it orthogonally on this, take the error, divide by the norm square of that, get one component and go on doing it. So, I can always construct. Okay. So, that means I can make the number of columns same as the number of rows theoretically, isn't it? So, in that case, I mean there is now no restriction on Q being rectangular. Okay. From here I went to, what is that? One more page was there, yeah, here. Just a minute. From here what I went to, I think this. Here Q was n plus 1 cross m, same as this, from a Q or minus R inverse. In this form, if Q number of columns increases. Number of columns increases, that is first m columns as it is, and then I generate the extra one by my own way. Then you got me m orthonormal vectors, but there are still some more left. If this way the total number of row is n plus 1, the vector space dimension is n plus 1, but you got me only m. So, n plus 1 minus m, so many extra vectors are to be generated. Then I get a complete orthonormal basis for that vector space. So, that I can carry out on my own, is not it? And again that is not unique. I consider the m and then take any one, remember the word any one outside the space spanned by those m fellows, take that, project it orthogonally on the space spanned by those fellows, that error will be orthogonal and then divide by its norm square to normalize. Again this is the m plus 1th component, again take this m plus 1 fellows, take the space spanned by them, go outside that, take another vector, project it orthogonally, take the error and normalize it. That way you can call, okay. So, this q can be made like this then, x 1 prime, sorry, x m prime, this is what we had earlier, and then extra vectors. These vectors are coming purely from my from whatever I got here, and that is why this side is not unique. This side is unique given the data x, and that way we generated that x 1. If you follow the stick to the data, you have to start with x 1, then take x 2, then take x 3, then obviously you get this, and on this side you get. But then this matrix becomes square. What will happen to R prime? R prime was a square upper triangular matrix. So, now that R prime we will have that chunk of zeros. You remember I brought the chunk of 0 here, it was just a, I mean silly mistake. I, without noticing that this is still rectangular and not square, I out of bad habit put the zeros here. So, there is nothing, this q can be this, okay. This generalized q you can say, q prime this will be your x, but this is unitary, this is unitary. So, if I pre-multiply both sides by q prime transpose, that is Hermitian, this will go, this will become identity, and so q prime transpose times x will be a matrix of this kind, where the top one is an upper triangular matrix and the chunk of zeros. That is what, how to get such q appropriately, I told Gibbs notation is one way which we will see. Okay, that technique, that algorithm of Gibbs notation I will come to later. Let us find relevance of this here. So, I will generate a square matrix. Now, there is no problem, this can be square. I will generate that qn which will working on this rectangular matrix. This is a rectangular matrix, total number of row is n plus 1, column is only m, but that will, this is a square matrix that will work on this, give you. So, this entire thing should be equal to of this form, one upper triangular matrix of the form R n, this is actually upper triangular, like this, zeros here. This often in papers and books, upper triangular matrix is denoted like this, the upper triangular, and there is a chunk of 0. This time C n. Now, see, things are very nice now. Consider this guy, this is working on a vector and giving me another vector. Okay, giving me another vector. This vector can have two components, the resulting product vector I can divide in two components, one component of this length m, another component the lower part, upper part, lower part. Okay. I will write down later, but upper part, some upper part, lower part, that minus this norm square of just usual norm square, not conventional norm square, because lambda has been put inside, that has to be minimized. This into C n, of course. Now, remember this part times C n will contribute 0. So, this lower half here of this vector minus this is independent of C n, that will always be present in the norm square. This is not I mean removable, and this upper half minus this into Cn can be made exactly equal to 0. You are solving equations only. Upper half part and upper triangular matrix with non-zero diagonal entries times Cn. If I suppose solve it, solving the equation is very simple and can be done by a systolic array. Upper triangular matrix, so first element times first element here is first element, find out the first element. Then use it here, first element, take the next one, like that. Solving is not problem. Okay? So, you can easily compute those optimal filter coefficients by this method. Only thing you have to compute this value, this vector. Let me put it then in mathematical form. So, this into, so this quantity was x prime n, q prime n, this quantity is C n, and suppose you write q n as 2 part. This q n matrix, one upper part that will work on this, give you the upper half, lower part work same vector will give you the lower part, upper part, lower part. Okay. Q upper n, q lower, have I used L somewhere? No, q lower n. Okay. This is your m cross m, and this is obviously you know the total length, I am not writing it here. Okay. And then q n, what I have just now said, I am just writing in mathematical, using mathematical symbol into this. This can be what? This matrix you write like this. So, it is upper half times this vector will be here. You can call it, I have not used u anywhere today, no? Have I used u vector anywhere today? No. So, I can u n upper vector and this is lower vector L n. Okay. There is u n is, what is u n? In q n, the upper part times this vector. This simple matrix multiplication, the upper part times, that is q u n times this guy. And L n is okay. With this definition, this norm square, this total norm square thing becomes equal to, this entire thing becomes equal to what? Mind you, this norm square is the usual norm square, lambda is no longer present, I have taken care of lambda inside. This is a conventional norm square. This norm square means what? Total vector, find each term square, all the terms add, out of which this guy from this side, the lower half times C n will give rise to chunk of zeros, that subtracted from L n will give rise to L n only, and upper half. So, that means this total norm square will be plus this part u n minus okay. This guy I can always solve this. R n is invertible, R is non-zero diagonal entries I told you. So, you can solve it, and solving that will not take much time. It is a very structured matrix, upper triangular. Okay, only thing is it will lead to a systolic array actually. First you obtain the solution for the first guy, use that. So, that is a pipelining mechanism. In the first cycle, if you find the solution for the first entry, next cycle you go for finding the solution for the second entry using those next two elements. Okay. Then use those two solutions to find the third. It is a sequential thing. So, that can be pipelined. We will see in detail, that will actually give rise to an array, systolic array, but you can see this, there is a sequential way and very fast then. Okay. Once you solve that, that means this is equal to 0. And this is the norm square. This is the problem. Now, problem is I got Qn somewhere or other, say. At index n plus 1, again I have to find out, I need new Qn plus 1. I will get a new solution for Cn plus 1 then. But if I do manually every time, then it is ridiculous, we cannot do that. This process has to be made adaptive. From previous Qn or current Qn, by some simple calculation, generate the next Q, that is Qn plus 1. Though effectively we will not be computing Qn, we will be using, we will be computing, we will basically solving these equations. It has to, but it has to be made adaptive. So, we will be basically considering Given's rotation is one way, which is very effective here to have this QR decomposition, but there are other ways also. There is something called Householder transformation, there is something called recursive modified Gram-Schmidt. They all lead to various forms of adaptive filters, all lead to systolic arrays. Given's rotation is one way. These are all algorithms. QR is given. How there are various algorithms to obtain that QR. Given's rotation is one, which is very elegant. Physically, what is happening here? Can you see what is happening here?
Out of n, we are taking only, n of them is projected, so those we can equate to 0, but others we cannot.
Those other ones,
they are the projections.
Yeah. You are actually given a set of vectors, m vectors only, you are orthogonalizing them, and then going ahead further we are orthogonalizing. Then overall norm square will be norm square of those fellows plus norm square here. Norm square of those fellows that I cannot touch, but here I remain in the space, I can find out coefficients Cn, so that there the error can be made equal to 0. That is what is happening. Okay. When I go outside the space, I have no hand, that does not depend on Cn also, they are the equations. That is what is happening. Okay. So, 4 minutes. Rotation, no, though it is school level stuff, but I forget often. Suppose there is a vector x y, you rotate it by theta, you are here, x prime y prime. What is x prime y prime? You know all this? You know, or you know how to do this? You call the length p. So, this is, if you give this name alpha, p cos alpha is x, p sin alpha is y, and then here same p cos theta plus alpha is x prime, p sin theta plus alpha is y prime. Expand them and use those facts that p cos alpha was x, p sin alpha was y, and you get a formula. But what you get is this theta. This is the arrow, so theta could go in this direction also. Cos theta, no? Yeah, it has to be. I can see it from unitariness. So, you see in 2-dimensional world, every vector, when you rotate, you get another vector by this formula, where theta specifies the rotation angle. This is a linear operator. You can see it is unitary. Multiply by its transpose, you will get an identity matrix. Can you see this? If you call it, give it any name, pre-multiply by its transpose, cos square theta plus sin square theta will always be 1, and other is plus minus things will come up equal to 0. It is a unitary matrix. Now, rotating by theta in this direction, you all agree, na? It will give me the same thing. If I rotate, if I hold the vector as it is, and rotate this axis in the opposite, in the two axes, the system, 90, the angle will be 90 degree, they will be orthogonal, but the two are rotated backward by theta. Still the total angle will be theta plus alpha, and therefore, the x prime y prime values that will come up, they will be the same. Okay. In Given's rotation, Suppose we consider one vector, I am not even close to giving a student, one vector of length 3. Well, have I switched off mine? Good musical interruption. Suppose I have a situation like this. There are 3 axes and there is one vector given. I do not know pictorially, it might be, I do not draw this diagrams very nicely, that is my problem. Suppose it is given x, y, z. Okay. Just few minutes, you project it here, this much is x, this much is y, this much is z. Suppose this angle is theta and this angle this is that projection. So, this angle is theta, this line is in the plane xy plane, this is the xy plane, this is the xy plane and this angle say alpha. Suppose I rotate this vector backward by theta, backward I mean by theta as shown, because this vector could have been here also, backward forward I should not use, by the theta shown, or effectively I rotate this plane, this 2 axes maintaining 90-degree angle between them orthogonality in the opposite direction by theta first. What will happen? This will align with this. And therefore, this particular line will be in the x z plane then. Will be in the x, I cannot, they are not allowing me to draw it any further. So, I cannot draw, I will again pick up from here, x z plane, just hear me out, will be in the x z plane. So, it will be like this, you know, this is this, and this fellow will come in this plane, x z plane. Okay. So, now in this new coordinate system, this vector will have at least one coordinate equal to 0, isn't it? We have rotated. So, y one coordinate is 0. Then what will happen? You take the projection here of this fellow on this plane. So, this is the vector. Keeping this axis as it is, if I rotate these two now, so that this guy is aligned here, then finally what will happen? You know, what I am by this procedure, what will happen? This axis will finally come along this way rotation, then this way rotation. Okay. If that happens, then in the new coordinate system, it will be some value, then 0, 0. That is a 2-stage Gibbons rotation. This have to apply to other vectors also. I will pick up from here in the next class, 1 minute. So, tomorrow we meet at 3:30 here. I do not have time much, you know, I need some 2 hours at least to complete this interesting topic. Thank you very much.